Hi, my name is Tessa Maurer, and I'm presenting on discriminating single and pile-up pulses using an autoencoder and photon-active interrogation. Detecting special nuclear material is key to prevent the diversion of that material to clandestine states, and one important part of that detection is interrogation. We have chosen to use active interrogation over passive interrogation for a few reasons, but mainly because passive interrogation relies on delayed signatures, and active interrogation can detect prompt neutrons. Additionally, we have chosen to use organic scintillators to detect neutrons because, unlike detectors like helium-3, scintillators don't thermalize the detected neutrons. Still being organic scintillators are also sensitive to both photons and neutrons, but this dual particle sensitivity can present challenges in high photon flux fields due to the presence of something called pile-up pulses. This next section has more background on what I mean by that. First, because of that dual particle sensitivity, organic scintillators have excellent pulse shape discrimination capabilities. Figures 1a and 1b show how this process works. For a given total energy, figure 1a shows that a neutron neutron pulse plotted here in blue has a greater area under the tail than a photon pulse plotted in red. If you plot the tail integral versus the total integral for a myriad of these pulses, as shown in figure 1b, two distinct bands form, a neutron band and a photon band. If a secondary pulse is present in the pulse window, however, as shown in figure 2b, we see points between the bands and even exceeding the neutron band in the PSD plot, as we see in figure 2b. This makes identifying special nuclear material nearly impossible without eliminating all piled-up pulses and thus degrading our statistics, which will be quite a significant effect for active photon interrogation. Therefore, we have created, through previous work, an artificial neural network system to classify pulses from organic scintillators with capability to even recover those piled-up pulses, as shown in figure 3a. Now, a portion of this ANN system is to distinguish singles from piled-ups, called classify top. Cleanser 1 uses an autoencoder to independently verify the single pulse classification from classify top, with details shown in figure 3b. As seen in figures 4a and 4b, Cleanser 1 works by reconstructing each pulse using an autoencoder trained on true singles. The absolute difference between the reconstructed and original pulse is found, and the ratio of that reconstructed pulse to the absolute difference will amplify small ripples in the tail, making it clear to distinguish piled-ups and singles. Because small ripples, which are sometimes misclassed by classify top, result in increased tail integrals, particles are more likely to be misclassed as neutrons with an inaccurately high total energy. Figure 5a shows some example of pulses misclassed as singles by classify top that have small ripples in the tail. Figure 5b shows a PSD plot of passive californium-252 data in blue, and plotted in orange are LINAC pulses misclassed as singles, caught by Cleanser 1. Figures 6a and 6b show the energy spectra for the ANN attributed single neutrons, with and without Cleanser 1. On the left, we see that the active background neutrons don't exceed an energy of around 3 MeV, but on the right, where we do not use Cleanser 1, not only do the neutrons from the active background exceed 3 MeV, but the gap between the blue and orange is much smaller. Given the endpoint energy of the LINAC, we do not expect active background neutrons higher than 3 MeV, but because of misclassed singles not caught by Cleanser 1, we see infeasible neutron energies. Therefore, having two independent machine learning approaches, classify top and Cleanser 1, increases the confidence of singles classification, which results in more accurate energy spectra of neutrons.